I'm Teddy. I'm on the intrusion detection team at Facebook. So we look for intrusions across all the machines that Facebook developers use and all the machines that run the Facebook app, right? I'm a builder. I'm a classically trained computer science geek, but I love to study bootstrap technologies. I'm obsessed with firmware. Firmware, trusted computing, secure boot, everything that bootstraps like architectures, security primitives, and operating systems. I don't get to work in that day to day. I get to defend a network. So I try to take every opportunity possible to merge these two things today. I'm going to talk about how, as a defender, if there are any defenders in the room, if you're obsessed with firmware, just like I am, you can wrap firmware-related stuff into your defense of your enterprise, and hopefully convince you that that is something that we should be doing today. So firmware security has always been a really important topic, but we've seen a resurgence of interest in our community over the last 4 years. Why is that? Why are there so many talks about EFI, about SMM today? Well, if you think about how many development boards you've seen in the last month, think Arduinos, Minnows, Leafs, Pines, all of those things, are requiring you, the developer, to go out and build firmware. If we combine that with our industry, the software industry, plus industries like Intel, hardware industries that are embracing open source technology as advantageous, hopefully almost soon necessary, we get this really cool, awesome, epic opportunity. We, the developers, the defenders, the security geeks, get to play in the realm of firmware. So firmware, the intersection between hard and software, mandatory for a developer now, is becoming absolutely necessary. Raise your hands if you've built a grub, an eLilo. Have you compiled one, right? You're touching firmware right there. You're talking to the APIs that exit from UEFI and go into pointing the execution pointer to your kernel eventually, right? How many of us have written things to the MBR or even modified our BIOS as Slick? You modified a Slick, why are you doing that? Right, this is awesome, right? And this gets me really excited if you can't tell already. So for us too, there's a duality of interest here. We're attacking it, but we're also embracing it. We want to use firmware, we want to use secure boot to defend our machines, but we also want a vulnerability so we can jailbreak them, so we can run homebrew stuff on it. That's awesome too, because the vulnerabilities there within are used for good or evil, right? And if we can play as researchers to find good vulnerabilities that let us do fun things, that's a great area to motivate research. This is unique, right? This is unique and really exciting. So I'm going to try to suggest a strategy for all the defenders out there to wrap in firmware-related intrusion detection into your tactics and strategy today. Right? So I want you to go home, and I want you to look at some of the recommendations I have and start implementing them on your enterprise. We should be capable of detecting with the precision. We should be able to detect firmware compromises with the precision that we detect malfeasance in userland. All right? That's a big should, but that's what I want to convey today. It's a big should because all of the code that's running inside firmware, inside your bootloaders, is almost all killed before your kernel starts. So before your kernel starts and before the watchdogs and the daemons that you have to detect compromise start, all that code is gone. Now, people are going to call me out on that, but for the most part, the thousands of applications that run inside UEFI are gone from memory. As Andrew Case puts it, like the current way we do forensics just falls apart at this point. So this is the UEFI kind of block diagram represented in colors that I like. And on this laptop right here, I have 1,500 files, applications running before my bootloader takes over. Within that, there's over 100 lines of compiled code that we can't defend right now. Now you're going to say, Ted, you're wrong. We can defend that. There's things called trusted boot. You mentioned it. In the TPM 2.0 spec and the TSS, there's something called a measurement log where we can see everything that gets executed if it was measured. We can pull that measurement off, and then we can attest it. Well, Yes, but by the time your bootloader takes over, the measurement log of all the executions that you were measuring, if you opted in to measure it, is wiped out of memory. There's a really cool individual in the audience today who told me yesterday they were working on bringing that into the kernel. Go forth and conquer, please. But there's another problem here, and that's one of the things that firmware is doing is loading up execution environments that are completely opaque to us. A lot of the firmware vulnerabilities that you've seen over the past 2 years have used unsanitized input in something called SMM. So SMM, System Management Mode, gets populated by a UEFI. We put a lot of code in there. We structure it. We point an execution pointer somewhere inside the memory controlled by SMM. It wraps itself a little bit and then starts locking off regions of memory. It does those locks such that other modes, your rings 0 through 3, can't then go introspect into that. They can't write, they can't read. So now we have tons of code running before our kernel starts and alongside our kernel, and we can't introspect into any of it. And we are caused to defend it, right? So how do we do that? So this mainly applies to Intel devices. AMD has a similar kind of environment. ARM, if you're familiar there, has something called TrustZone. TrustZone is probably more equivalent to Intel ME, the management engine, or for newer systems or Atom systems, TXE. In there, you'll also find very opaque environments that we're charged to defend, but let's put them out of scope for right now. We have lots of code executing before the kernel, lots of code executing side by side our kernel. Yet, some will argue that this attack surface for these environments seems very small, right? And we all will compute associated risk while contending that attackers require outstanding sophistication to compromise these things. So Ted, why are you up there telling me that we have to defend them, right? Over the last 2 years, like I said, the 25 security presentations I mentioned, they are all claiming proof of concept exploits for these environments, right? It costs $100,000 to buy a rat to put it into UEFI, and it costs probably about that money to also find a vulnerability. So you purchase the vulnerability once, and then you scale your rat out into infinity. That risk is also magnified for us in the opposite direction. There's a big fragmentation problem with firmware, similar to Android, only a magnitude larger in the amount of code that goes into UEFI and several magnitudes larger of the amount of devices that are supported by OEMs. In May 2014, I created a little spider that went to all the OEMs I could think of and started downloading all their firmware. It just went to all their download pages, looked for anything that looked like firmware or a firmware updater, and download it, right? I got 50 gigs of firmware. After I kind of deduped that a little bit, I was at 21 gigs. So 21 gigs for about 2,500 devices. As of last month, that 50 gigs that I downloaded, if you run that spider again, is 80 gigs. And that's on GitHub too if you want to replicate that. Also send me an email, I'll send you that dump too. So out of that, most of it is updates, and they're trivial updates. They're 1 or 2 lines of code that are patched that require another 16 megs of download. So that's why I can reduce that 54 to 21. Within all of those updates are a lot of security patches. I hope everyone, before you think about doing compromise detection in firmware, is including BIOS and UEFI patches in your update, your vulnerability management cycle. If you're not, there are published attacks against the firmware running on the systems that you're charged to defend. So I'm going to scope this real quick. I don't want to talk about unmodifiable silicon. I don't want to talk about microcode. I want to talk about UEFI. I want to talk about all the SPI flash that UEFI boots from, executes out of. I want to talk about the embedded controller data on Lenovo laptops. I want to talk about updated bill of firmware on your video cards, early stage bootloaders, so the EFI bootloaders that you have on all your Apple machines, the Grub EFI bootloaders that you might have on your I think there's a ThinkPad back there, and of course all the configurations that go into this, right? So within that scope, there's tons of security primitives, right? there's tons of things that initialize, like the full disk encryption, entropy input, your network card if you're PXE booting, the signature checking on all of that. Remember, these are the things that bootstrap awesomeness, like the awesomeness we get in repeatably built tours, the awesomeness in credential stores, right? I want to target all of that foundation code, right? Now, as we've seen from Google's Project Zero and their focus on AV over the last couple of months, the tools that are designed to help us to reduce our risk may actually introduce it. So when we're looking at these things, when we're bringing technologies, when we're bringing code into scope, always ask the question, to what extent have those developers that you're implicitly trusting gone through code reviews? And when they have proprietary code, why is it proprietary? Why is it closed source? So I would extend that. I would extend that to say, why can't we get firmware open? Why me, as someone who has to defend tons of computers that run Facebook, why am I subject to running binary blobs on these systems, right? That depends a lot on the people, a lot on culture, a lot on our attitude. Very difficult to protect or to perfect, but hopefully over the next couple of years we can get there. Totally open firmware systems. So, you know, I want to put these environments under a really awesome microscope, a really dense microscope. And I want to be diligent too, because the people who are working for these OEMs, these OEDs, and these vendors, they have a hard time shipping this code. And we should take every opportunity we can to help them, right? If we're purchasing tons of machines that have binary blobs, we're probably sending them a lot of money, which means our voice carries louder than others. So if we have the opportunity to get in there and say, hey, let me help you with this, let me help you ship open code, they'll be really receptive, right? And that's not just the people we purchase from. That'll be all of you in the room too. So our goal should always be to help our vendors ship safe products. So the attack surface I mentioned earlier for UEFI, what does it look like? If a vendor doesn't check signatures on firmware updates, I can escalate on your machine. If they're not checking authentication on update channels, then I can like remotely infect your machine. So over the last month, if you're looking at the firmwaresecurity.com's blog, you'll see there's a couple of tools that weren't checking certificates. They just have like curl-k kind of stuff here. That allows for remote intrusion. There is even a bigger problem here, and some of the repositories where firmware comes from also is not protected. If you find one of those, that'll allow for mass infection. So please, please, please tell that vendor quickly to go and lock down like the FTP in which they serve their firmware from. And then from the security conferences, we see vulnerabilities in update channels. We see vulnerabilities in secure boot implementations. Those will allow for one or two, right, for the escalation or for the intrusion. So out of the top 12 vendors out there, by device count, 3 of them, out of the 12, 3 of them still do firmware updates over unauthenticated channels. One of those has an intersection where they're not doing signature checking too. So all devices by that vendor are susceptible to remote compromise. All I have to do is man in the middle of your network. And out of the 25 presentations, there's contained 40 0 days in the update mechanisms or channels, all produced by 10 researchers, right? So keep that context in mind. I have a lot of applications running on my laptop in UEFI, all of which are linked against a OpenSSL version 0.98, which was just deprecated last month. It's not a problem right now, but if we let those things kind of sit, they're going to be problems. There are memory handling issues in X509 in the firmware that I have here. Not attackable, but just problems that left unchecked will be really hard for me to defend my enterprise. So simultaneously with that motivation to vendors and developers, my Defender brothers and sisters out there, let's take this scope and apply it to detection and compromise as best as possible. So we're going to do 2 things. One, we're going to push on our vendors in a very nice way, and 2, we're going to apply some techniques I'm going to show you right now, which we use at Facebook. So before we even get into firmware, I want to talk about kernel extensions. So kernel extension on OS X. If I'm going to collect all the extensions that are loaded across my enterprise, I want to aggregate count just the path names of them, and then I want to ascend sort. So I have the top 10 unique. I want to grab each one. If you can do this on your enterprise right now, you are sitting pretty, and you're ready to advance. So here, from the 12,000 desktops and laptops that I have to defend, these are the top, the most unique. If you find something called direct hardware, maybe someone's doing research, maybe someone's trying to read physical memory from your machines. If you find that, let me know. If you find that, probably take it down. Next, I want to look at the kernel path. So the kernel path, the cache on OS X, is very well known. We have file integrity monitoring solutions. I run one that I kind of write called OS Query, and I pointed at all of the EFI, and I pointed at all the kernel versions, and I can see when anyone updates their kernel. I should see this in tandem across the entire enterprise when a new version of OS X comes out. So this is over the last week, just this week. I see tons of people updating to 14.3 and tons of people updating to 15.4. That makes a lot of sense. I see nothing kind of lagging behind, maybe one or two devices that are just coming online, maybe loaners. This is awesome. I like to do this. This is really easy to check for kernel extensions or for kernel modules. If you're going to get attacked by a rootkit, you're like, Ted, you're going to get attacked by a rootkit. They're going to hide all of the syscalls that you're using to check these locations. Well, deploy it today, and when that rootkit comes along and establishes an IO-controlled character device inside of dev, you will see it pop up. You'll see the kernel rootkit as it is trampolining all of those syscalls. And that's good enough for me. If I can get all that data, I can react pretty quickly. So over this last week, I looked at all of the new device nodes that came up on my enterprise, and here's what I found. I researched all of them. They all look really good. Shame on whoever named the hardware accelerator for Android devices HACS. All right, so whoever wrote that and thought it was a good idea, you made me like poop my pants. So, gosh. That was crazy. Here's all the bootloaders. So these are organized by hash. I didn't actually put the MD5 or the SHA-256 up. But what's odd about this here? So I saw 2 updating kernels over the last week, and I'm seeing much more variance inside my bootloaders. So the one on the top here is actually someone experimenting with a couple machines trying to optimize a bootloader. The one in the middle there is me. So I was just testing to see if I could find a bootloader. There's an OS X example bootloader on GitHub that you can go out and compile yourself. You can put in a little exfiltration of the full disk encryption key there. You can deploy it to a machine, and you can see if your file integrity monitoring picks up. Works awesome. So I would propose that these are really easy things to do, and Intel will back me up that they're really important things to do. In their 2016 threat predictions, they say that firmware attacks are going to amplify. Now, I understand why they're going to say that. They have big teams that are researching this. But if you think about cloud computing, too, if you think about all of those virtualization technologies, firmware attacks are ripe for doing lateral attack or for escalating outside of virtual machines. So money invested into firmware attacks is not only going to be targeting our enterprise, but also these, and we're going to see the backflow from it. So these things, the file integrity monitoring and the hashing that I just showed before, they deteriorate pretty quickly when I try to go below the bootloader. So let's step onto the shoulder of giants and look at Intel's ChipSec and MITRE's Copernicus, right? 2 tools that are designed to dump flash, pull it off so that you can hash it. So can we introspect into firmware from userland? Those 2 things that I mentioned, they both come with pretty big warnings. Those warnings include, do not use this in production. So from userland, from a stable deployment, can we check firmware? Not really. We can't really do that today, and I'm kind of hard-pressed to push out kernel extensions or kernel modules just to read a bit of flash. So what I want to do is kind of get close without compromising the stability of my systems, right? So let's look at ACPI. ACPI tables are another thing that we can check variance of. It's really hard to determine what I'm putting up here, but this is over those 12,000 laptops, and these are all the counts of ACPI tables and then the unique hashes that I see. The ones at the end kind of stick out, even more so when I graph it. The ones at the end here are probably unique devices, or they're devices with unique hardware attached to them. I can take that and I can join it against SMBIOS. So SMBIOS will report the version of firmware that's supposed to be on these devices, as well as all of the hardware that should be attached. When I make this correlation, I can cross out the bottom there and say that this is unique hardware, this is not an attack. I can also do it across my PCI device ecosystem. So I can look at all the PCI devices on my laptops with OS Query. This is a select star from PCI devices. And I can see if that data inside the ACPI is backed up by the PCIs that are attached. So over our enterprise in the last week, I noticed 30 PCI devices that were only observed once, right? So laptops, they experience a lot of noise. When you do this on servers, they experience little to no noise. You do this for USB too. On your laptops, lots of people attach USB. This is common. On servers that are in data centers, no one should be attaching USB. This is instant signal for your defenders. So also in userland, EFI variables are reported. The EFI variables that select the boot device that your computer is going to boot, as well as the file on that device. It also controls things like security primitives. On OS X, if I want to disable SIP, I can write an EFI variable that turns it off. Or I can write a flag mask that turns off specific features. Now, when I watch these variables change over time, I can watch every developer who's turning off SIP. I can watch every developer changing their boot device or something else trying to change their boot device too. So I take this data and I join it against all of the EFI hashes that I saw, as well as the kernel versions that I saw. I can now reduce the noise of things that are induced by updates or things that are induced by developers actively trying to replace their bootloaders. So for these two here, I see SMC flasher results. So someone just updated the SMC flash on their OS X. I can also see when a kernel crashes. I get the stack trace. So if I want to do any sort of vulnerability detection or vulnerability research, here's a ton of stack traces that I can go investigate. Awesome, right? And that's actually led to a couple of submissions to Apple. So all this data that I showed is available in the OS Query tool. I run all of these queries that generate this data all the time. All this data was just pulled from this week. I want to release all the queries that I use to build these visualizations, as well as the join, so you can pull the signal out. And I want to make them all available to you following me getting off this stage. So if you do have an OS Query deployment, or you have OS X or Linux machines that you want to defend, install this tool. It's a userland daemon. It pulls all this data out, and it will send it to your aggregator. It's our logo, and it's really easy to interact with it. So if I wanted to look at this device for a Thunderbolt adapter that I just attached, I could really easily select from PCI devices, exclude all the devices from Intel, and out pops 3. The last one is a Thunderbolt device that was attached. If I want to see all the events that happen over time, I can look at it in the event stream. So with all operating systems, they usually have some sort of API layer where you can get hardware events. If we attach to that, now we can slurp up all hardware events for OS X, for Linux, and Windows very soon. So I can see that that PCI device being attached at a time. If I then see that a device was compromised by a firmware attack, I can do the exact DIR process, go back and reconstruct the attack with the events, and plus all this metadata that I've been pulling out. So we're always going to add more stuff related to firmware. I told you I was obsessed. Hopefully my enthusiasm on stage is corroborating that. These are the tables that are available right now to do this sort of firmware components incident response and intrusion detection. I want to increase this double by this time next year. So there's new creative things that I can look for from userland. There is kernel extensions and there are kernel module. So reading Flash in a really repeatable and safe way is on my docket too. So one last release, one last thing I want to talk about. I have nothing to do with VirusTotal. We worked with them over the last couple of months to add firmware parsing into VirusTotal. I'm super humbled to be up here and to announce this, that you can take a firmware update or that Flash that you read from your device and send it into to VirusTotal. This is the firmware that I run, the UEFI that I run on my Mac right here. And this is it pulling out all the metadata about it, the time that it was compiled, who and on what machine it was compiled, the device that it was compiled for, and More specifically, if you can see this on the screen, it's pulling out every embedded file, all those 1,500 files that were in there, and it's checking the hashes to see if anyone ever updated it or uploaded it here. So if anyone marks these as malicious, now you have instant signal to check against. And I think this is another theme that I want to pitch today. If you're developing tools that are in the pipelines for defenders, and you're interested in firmware, or you want to send me an email, I will gladly help you try to integrate firmware parsing, try to integrate detection of weirdness into that tool. So soon we'll get attestation. That'll be amazing. I still think that's a couple of years out before it's made available to everyone. But remote attestation is going to take us from all the defense and the detection that we're doing right now and multiply that threefold and give us really good signal when something goes out of bounds immediately. Until then, let's continue this deep system forensics and wait for the two to definitely complement each other. Thank you so much, and I would like to take about 5 minutes worth of questions.